So the next lecture in this unit is on diffraction gratings. It's going to be section 10.3 in your textbook. Now, when we looked at the double slit experiment, we were basically, we had the single source of light and it fell on a double slit and it produced that, that interference pattern. What a diffraction grating is basically if instead of a double slit, we used something with multiple slits, and that is what we call a diffraction grating. So if it has multiple slits, we're actually going to see a wider interference pattern, and by doing that, we can analyze things a little bit differently. Although you'll see it's essentially the same as a double slit, but a diffraction grating is easier to produce than a double slit. Now, some natural diffraction gratings would be the grooves on a CD that you see in this picture here, or the shimmer that you see on some animals, like this indigo snake that's shown in that picture. So it says it's difficult to measure the wavelength of light accurately using the interference pattern from either a double slit or a single slit. So with a double slit, we're limited on the number of fringes we have, bright and dark. For a single slit, again, we're limited. A diffraction grating will give us much more slits, which makes it easier to measure. So the principle on which diffraction grating is based is the same as that of the double slit. So the diffraction grating simply has thousands of pairs of double slits that work together to create very fine, bright fringes that are separated by large, dark fringes. So we often define diffraction gratings by how many lines per centimeter they are. And that D value, that's the D value. Basically, that gives us what our slit measurement is. So for a diffraction grating that has 2,000 lines per centimeter, the slit spacing would be 1 over 2,000. So we reciprocate 2,000, and we end up getting D equals 5 times 10 to the negative 4 centimeters. So when M and the path lengths of all the rays are the same, the rays go directly through the grating, creating a central bright fringe. The next bright fringe above or below the central fringe is called the first order fringe. The naming continues with second order, third order, and so on. So we have two types of diffraction gratings. We have transmission gratings, where the light just passes through the slit, and we have reflection gratings, in which light is reflected by smooth lines separated by non-reflective surfaces. So the ones we see, the ones you would have seen would be the reflection gratings, like the CD, or an animal like a snake that has kind of an iridescent sort of look to it. The one we use in physics, in terms of physics labs, is usually the diffraction grating, where we look at the slits and we look at the transmission interference pattern, and we observe the fringes and how they basically how they're lined up. So it's easier to make measurements is basically the idea behind a diffraction grating. And to show you how it's easier, let's look at a series of slits or a series of slit experiments here. So this image isn't very good, but the first row is a single slit. So you have that central bright fringe, and then you have other fringes there. So you can count 3 bright fringes. When we add a double slit, you start to see more fringes occur. As we go all the way up to 7 slits, the bright fringes start to resolve into closer to straight lines. And if we have a diffraction grating with a lot of slits, we end up seeing the interference pattern appears to be very, very sharp straight lines. So please copy this down for a diffraction grating. One thing to note, most importantly, D equals 1 over N, where N is the number of lines per centimeter. I think on your formula sheet it says for diffraction gradient, I think there's a comment saying use the double slit experiment or use the double slit interference equations. That is true, except you have to find your D value, which is 1 over N. So let's look at the first problem here. It says light with a wavelength of 500 nanometers is incident on a diffraction gradient that has 8,500 lines per centimeter. And we're asked, what is the spacing of the slits? So here, the first thing we need to do to find the spacing of the slits is to find out what 1 divided by 8,500 lines per centimeter is. So I divide 1 divided by 8,500 and then divided by 100 because I have that's in centimeters. I get 1.17 or 1.2 times 10 to the negative 6. If I'm reporting this answer down, I write down the 1.2 times 10 to the negative 6. But what I'm going to do here is I will store this in memory so that I can recall this, because I need to use the exact value in my calculations, not the rounded approximate value. Let me just move this over here. Now it says to calculate the angles of the first two maxima. So if we're looking at the maxima, that means we're using the constructive interference equation. And I guess I will, I'm going to show this on the page here, but I'm going to make it a bit smaller here. So to solve this, what I'm going to do is I'll write down the equation first. So my equation is m lambda equals d sine of theta m. And I'm going to rewrite this in terms of theta m. So this becomes m lambda over d. So theta m is the inverse sine of m lambda over d. So that's my full equation. Now I'll do theta 1, which is the inverse sine of 1 lambda, which is, it's up there, 540 nanometers. And my d was that 1.2 value, but if you recall, it was 1 over 8,500 times 10 to the negative 2. So this is how I would write it being substituted in. But to calculate it, I do have it stored in memory. It's here. So what I will do is I will do 540 times 10 to the power of negative 9. And I'll divide that by my stored value here, which is 1 over 8,500 centimeters. This is the value I get, and I will inverse sine that. I get 27 degrees. So theta 1 is 27 degrees. Now I'll find theta 2, which is basically going to be the same calculation, but now I have a 2 in here. This is going to be 2 times 540 times 10 to the power of negative 9 divided by my stored value here. And I inverse sine that. I end up with 66.6 or 67 degrees. Let's look at another problem. This one says light emitted by a particular source is incident on a diffraction gradient with 9,000 lines per centimeter. It produces a first order maximum at 32 degrees. We're asked to determine the wavelength of the light. So first let's rearrange the equation. So my equation again, to start with, m lambda equals d sine of theta, and this is for a maximum, so it's theta m. I need to rearrange this to find my lambda, which is simply d over m sine theta m. My d in this case is 1 over 9,000. 1 over 9,000 centimeters. And that whole thing over my my m, which is this a first order? Yes, it is. So it's a 1. And then I have sine of theta m, and theta m in this case is 32 degrees. Now here I'm given, I would argue that this 9,000 limits us to 2 significant digits. It looks like the answer is given in 3, but we'll just write it in 2. Okay, I realized what I did wrong here. Basically what we need to do, I forgot that it's lines per centimeter, so this is actually in the numerator. So what I'm going to do, I'm going to rewrite this. Lambda equals d, which is 1 over 9,000, and my centimeters are up here. So that becomes this whole thing divided by 1 because of the m, sine of 32 degrees. And if I calculate this, it becomes 10 to the power of negative 2 divided by 9,000 times 32 sine. And I get 5.9 times 10 to the negative 7. So here it says, consider 2 diffraction gratings, one with 8,500 lines per centimeter and one with 10,000 lines per centimeter. Compare the separations between adjacent maxima for these gratings. So we need to find the delta x. Now, to do this, what we're going to do is let's find it's adjacent maxima. So we're going to write the delta x equation for maxima, which is lambda. Actually, they're given there. We can start with this. Lambda is equal to d delta x over L. And rearranging that for delta x, we end up with delta x equals lambda L over d. Now, our d, for comparing these two, in one case, our d will be 1 over, so actually our d is 1 over n in both cases. So let's write this in terms of n. It's L lambda n. So in one case, we're going to have this n value being 8,500 centimeters. The other case is going to be 10,000 centimeters. So basically, what we're going to find is the spacing between the maxima will increase as this n increases. So if we're going to compare the gratings between them, or how many, what the spacing is, so let's do the spacing for the 8,500 lines, or sorry, let's write this as a ratio. Spacing for 8,500 divided by the spacing for 10,000 works out to lambda L 8,500 centimeters divided by lambda L 10,000 centimeters. This works out to a difference here of basically 8,500 divided by 10,000, which is 0.85. So the spacing for the 8,500 is 85% of what the spacing is for the 10,000, meaning that the more lines we have, the greater the spacing between adjacent maxima. Okay, we're going to move these out of the way so that we can go back to reading here. So it says, for a given diffraction gradient with constant slit separation, the angle that results in constructive interference depends on the wavelength of the light. Since different colors have different wavelengths, colors are separated when light passes through a grating. So what would you see if only the colors red and yellow pass through the grating? So basically, if we had white light, it would look like the top part where we have our white light, and then our maxima would be white. But if we break it up into the rainbow, basically, of that composes white light, we would see those component parts. If we only had red and yellow, in the central maximum, we would see a combination of the red and yellow. But for the other maxima, we would only see the red and yellow portions of that white light, or rather of the light, because it's being separated. So this makes diffraction gratings very useful, because now we can see what type of light is being emitted down to the hundreds of nanometers, or down to the nanometer actually. So one application of this is a spectroscope, and spectroscope uses a diffraction grating to separate light into the very narrow bands of specific colors, so that we can analyze the light. So in chemistry, you might have learned that certain compounds or chemicals, as they are heated, they give off light, and we can actually, that light that they give off is a specific signature of that compound or chemical. So we can actually determine which chemical is being emitted by observing the light that's being emitted when it's engaging in a reaction. So here's an idea. If we have a gas that's being heated, or we have some sort of electrical discharge that's passing through it, it'll emit a light that has a very specific wavelength. Now, if we pass this through a slit and then a prism, which acts as our diffraction grating, we would get what's called an emission spectrum, or often it's called a line spectrum, because the spectrum itself appears as lines of the different component colors that are being emitted. This can then be used to help us define what the gas is. This slide says, since atoms and molecules can absorb light at the same wavelengths at which they emit it, spectroscopes can also analyze absorption spectra. So we can also analyze what light is being absorbed by the atom or the molecule. And that light being absorbed will be shown by seeing certain bands of color that will be absent from what's called the absorption spectra. So this tells us what light has been absorbed by observing the light that is not present. So the sun's core emits a continuous spectrum, but atoms and molecules in the sun's outer atmosphere absorb specific wavelengths, causing the sun spectrum to have several narrow black lines. Therefore, by identifying the wavelengths of light that have been absorbed by the sun's outer atmosphere, physicists are able to identify the atoms that are present there. So we can actually see that because the sun is really a fusion generator, we can see what light is being absorbed, and we can tell what is basically being fused in the center of the sun. So we can tell what atoms are present there by observing that. So careful analysis of the sun's absorption spectra reveals that at least 2/3 of all elements present on Earth are present in the sun. In fact, this technique is used to identify the composition of stars throughout our galaxy. So you can copy this down for a spectroscope. It is a device that uses a diffraction grating to separate light into fine bands of color. Since each element has a specific emission spectrum, the resulting spectrum is used to identify the atomic composition of the light source. It says astronomers use absorption line spectra to determine the composition of stars. And then we have a spectrometer. This is similar. It's a device used in chemistry and biochemistry to identify and measure compounds and solutions. A spectrometer has a diffraction grating that separates white light into all wavelengths. So you can select a specific wavelength and send it through a sample of a solution. The spectrometer then measures the amount of light of the wavelength that is absorbed by the sample, and you can then calculate the concentration of the compound in the solution. So last thing to copy down, a spectrometer. So this is a device that has a diffraction grating that separates light into all wavelengths. It's used in chemistry and biochemistry to identify and measure compounds in solutions.